All right, welcome everybody to the next installment of the New York Combinatorics seminar. Today we'll have Seong, who will tell us about the nucleus of the Grassmann graph.
All right, thank you, Deepak, and thank you everyone for coming, and also thank you for organizing this awesome seminar. Today my talk is going to be on the nucleus of the Grassmann graph. This is a joint work with Professor Lee in Florida and Professor Park in Korea. Okay, so let me see if this. Nope, that does not.
Oh yeah, you gotta move the mouse.
Oh, there you go.
Click and then it's now hit.
Okay, there you go. Okay, so here's a quick outline of the talk. So we're going to go over a quick representation theory, and then we're going to talk about a subconstituent algebra or a Terwilliger algebra of a graph, and then we're going to talk about the irreducible T modules, and then we're going to go into the definitions of the Grassmann graph, the displacement, and what is the nucleus. Okay, so let's start with the basic idea of representation theory. So the most fundamental question that we ask in representation theory is find all symmetries of the equilateral triangle below. And in that case, we have 6 possible symmetries. We have like a bunch of rotations and we have a bunch of reflections. So like I said, there are rotations and reflections, and we can actually write them using a 3x3 matrix as the following. So we have a rotation of nothing, so this is the identity, and hence we have the identity matrix. So you can think of a 3x3 matrix as rows and columns indexed by the letters A, B, and C. Okay, so in this case, we're not doing anything to the triangle, so this corresponds to the matrix, identity matrix. And then if we have a rotation by 120 degrees clockwise, then we can write that as a permutation matrix that looks like the following at the bottom. So for instance, A goes to wherever C was. So the first column would be 0, 0, 1. And then B goes to wherever A was. So the second column is going to be 1, 0, 0, and then so on and so forth. So what we can do is for every symmetry that we have on the equilateral triangle, we can actually write it as a 3x3 matrix like the following. And then we have a bunch of flips, so the reflections, and then as such. Okay, so these 6 matrices, permutation matrices, you can actually consider them forming a group. So we have a group of following permutation matrices, and instead of those matrices acting on a triangle, now let's think about the following question. So consider a vector space V over the real numbers that is spanned by the basis, let's say A hat, B hat, and C hat. So instead of the vertices of the triangle, we're looking at some vectors on a vector space. So now the question is, how do the permutation matrices act on the vector space V? And the most fundamental, another fundamental question is, what are the subspaces that are fixed under the action of this group? So in that case, the most obvious vector you can think of is the 1, 1, 1. So the vector 1, 1, 1 is fixed by all those 6 permutation matrices, because you can think about it as a triangle, as no matter how much it rotates or no matter how much it flips, the span of 1, 1, 1 pretty much stays the same. And if the vector 1, 1, 1 is an invariant under the 6 matrices, then the plane that is perpendicular to the vector 1, 1, 1 is also an invariant. So the subspace, the 2-dimensional subspace A plus B plus C is equal to 0 is another invariant. So in representation theory, we commonly do this thing where we look at the elements of the group, see how they act on a vector space, and figure out what the invariants are, like the invariant subspaces are. Okay, and we have this famous theorem by Maschke that says every representation of a finite group G over R is a direct sum of irreducible representations. Meaning this action of G on a vector space, we can actually break it down into a direct sum of irreducible subspaces. Irreducible invariants, irreducible invariant subspaces. So for example, in the previous example, we split up that 3-dimensional vector space into a span of 1, 1, 1, and that 2-dimensional vector space that is perpendicular to 1, 1, 1. Okay, so far we have discussed a group acting on a vector space. So our next goal is going to be to discuss a subconstituent algebra. It also goes by the name of a Terwilliger algebra of a distance regular graph that acts on a vector space. So in a bit, we're going to define what a distance regular graph is and its corresponding subconstituent algebra, and we'll see how that acts on a vector space. Here is a quick photo of myself and my advisor, Paul Terwilliger. So the algebra is actually after him. He recently turned 70, and then we actually had a birthday conference for him in Slovenia. Yeah, unfortunately, I couldn't go because of like political reasons, but let's not talk about that. Yeah, but yeah, so the algebra is named after this guy. Okay, so here's some preliminaries. Okay, so we let gamma denote a connected graph, no loops or multiple edges. Let's call the vertex set x and the path length distance function partial. Okay, and the diameter d of the graph is the maximal value of the partial of x and y. So for any two vertices x and y, its maximal distance, or the maximum that you can obtain for the distance of x and y would be the diameter of the whole graph. Okay, now let mat(xc) denote the C algebra that consists of the matrices where rows and columns are indexed by the vertices, or the vertex set x, and all the entries are in C. So it's going to be a size, the size of the vertex set by the size of the vertex set matrix algebra, where the entries are complex numbers. Okay, now let V denote a C vector space that consists of the column vectors with rows indexed by x and all entries in C. And as you can see, the algebra, the matrix algebra mat(xc) is going to act on V by left multiplication. And this mat(xc) module V, we usually call it standard. Okay, now for a vertex x, let x hat denote a vector in V where x entry is 1 and other entries are 0. So we have a vector 0, 0, 0, 0, 0, and then we have 1 at the x entry and then 0, 0, 0, 0, 0. Okay, and we observe that V, the vector space V, is going to be a span of all these x hats, where x's are the vertices of the graph. Okay, now we have a definition of a distance regular graph. So we say that the graph gamma is distance regular whenever for all numbers h, I, and j between 0 and the diameter d, and all vertices x and y such that their distance is h, the number of vertices that are I away from x, so looking at the diagram, we have the number of vertices that are I away from x and j away from y is a constant that only depends on h, I, and j and not on the specific choices of x and y. So the distance regularity is basically giving us some sort of a symmetry of a graph. And some nice graphs that have this property would be, for example, like a cube or like any hypercubes. And as we will see in a bit, we're going to see a Johnson graph and the Grassmann graph. Those are also distance regular. So if it's hard to get the head around like what it means to be distance regular, just think of it as like it's a very nice symmetric graph. Okay, so now we talk about a Bose-Mesner algebra M. So this is going to be some sort of a sub-algebra inside that mat(xc). And we also call this like an adjacency algebra, if that's a little more intuitive. Okay, so for I between 0 and d, we define the matrix AI as follows. So for vertices x and y, the xy entry of AI is going to be 1 if the distance between xy is I and 0 otherwise. And one thing you note is that if I is equal to 1, we usually call this the adjacency matrix. Okay, and we're going to let M denote a subalgebra of mat(xc) that is generated by these adjacency matrices AI. And we call M the Bose-Mesner algebra of gamma, probably after two guys, Bose and Mesner. Okay, so let's look at an example of a Bose-Mesner algebra of a 2-cube. So this is what a 2-cube looks like. And let's actually label the vertices A, B, C, and D. And let's say the matrices are indexed or labeled so that each row is indexed by A, B, C, D respectively, and each column is indexed A, B, C, D respectively. In that case, A0 is just going to be our identity matrix. A1 is going to be the regular adjacency matrix that we usually see of a graph. And then A2 is going to be a graph where the entry is 1 if the distance between two vertices is 2. So for instance, you notice that A and D are distance 2. So the AD entry would get 1. And you can see that BC is also distance 2. So the BC entry of A2 is going to get 1. And then so on and so forth. So the matrix algebra that is generated by these three matrices would be the Bose-Mesner algebra of a 2-cube. Okay, so now that we have a Bose-Mesner algebra, let's talk about the dual of a Bose-Mesner algebra. So in that case, for the dual Bose-Mesner algebra, we have to pick a certain vertex x. So we pick a certain vertex x, and then for I between 0 and d, we define the diagonal matrix EI star, which depends on that pick picked vertex X as follows. So for a vertex Y, the YY entry of EI star is going to be 1 if the distance between X and Y is I, and 0 otherwise. So you can basically think of it as we have the regular adjacency matrix. We grab the Xth row, and then we grab all the entries, we tilt it 45 degrees, and then plug it in for the diagonal entries. That's basically what That's what E1 star would be, for instance. Yeah, so in general, like EI star, just grab A sub I, grab the Xth row, tilt it 45 degrees, plug it into the diagonal entries. That would give us the EI star. And we call EI star the ith subconstituent matrix with respect to X, because we're basically looking at all the vertices that are distance I away from X, technically. Okay, and we're going to let M star denote a subalgebra of matrix C that is generated by EI star, and we call this the dual Bose-Messner algebra of gamma with respect to X. Okay, again, let's try to look at an example where we have a 2 cube. Okay, so in this case, we're going to pick a vertex D on the right. And once we have that, E naught star is going to be a diagonal matrix where only the DD entry is going to be 1, because D is the only vertex that is distance 0 away from D. E1 star is going to be 1 for the BB entry and the CC entry, because B and C are the vertices that are adjacent to D. And E2 star is going to have AA entry 1, because A is the only vertex that is distance 2 away from D. Okay, so we talked about the Bose-Messner algebra and the dual Bose-Messner algebra with respect to a vertex. Now, you combine them, and then you get the Terwilliger algebra. So let T denote a subalgebra of matrix C that is generated by both M and M star, the Bose-Messner algebra and the dual Bose-Messner algebra. So we call T the subconstituent algebra, or the Terwilliger algebra with respect to X. So it's funny how Terwilliger himself is the only one who's calling it the subconstituent algebra, and all of us call it the Terwilliger algebra. He's just being modest and humble. All right. Okay, so we have this Terwilliger algebra. Now we recall the standard module V. It was a vector space where each row was indexed by the vertices of the vertex set. And by construction, V is going to be a T module. So the matrices in T, they're going to act on this vector space V. Okay, now we say that a T module W that is inside V is irreducible whenever W does not contain a T submodule other than 0 and itself. So basically, we cannot break W down any further. That's when we say that W is irreducible.
To clarify the question. So the mat C would be like you're adding just dimension just n squared or something like that. That entire thing.
Right. Yeah. The dimension
squared, and this is some lower dimension. This algebra.
Yes. It should lower than or equal to basically
n squared. It could be n squared or.
Good question.
Probably not.
Probably not. Yeah, because like basically the vertices that are the same distance away from D act as like a single chunk. So those things, I would imagine that they would have like a single dimension instead of like all the possible dimensions that you can get. Yeah. But yeah, thank you for the question. Okay, so yeah, we just defined the irreducibility of a T module. Okay, and just like how we had in the Maschke's theorem, it's a fact that the standard module V is actually a direct sum of the irreducible T modules. Okay, so here's a question. How do we actually classify, or how do we visualize the irreducible T modules in V? Okay, so let's go back to the example of a 2 cube, which is like one of the simplest examples. Okay, so we have 3 matrices in the Bose-Messner algebra and 3 matrices in the dual Bose-Messner algebra. Okay, now with respect to D, the irreducible T modules are going to be exactly these things. So we have one 3-dimensional irreducible T module, which is spanned by a vector A, a vector B plus vector C, and a vector D. And we have this 1-dimensional vector space, which is a span of the vector B minus the vector C. Okay, now unfortunately, so we have a 3-dimensional space and a 1-dimensional space. The dimension of the screen is not big enough to actually visualize the whole thing. So what I'm going to do instead is on the graph, I'm going to locate where these vectors, like the participating vectors, are located. So for instance, this is what this is what it's going to look like. So we have a span of B hat minus C hat. So we're going to put a red dot at the location of B and C. And then for this other irreducible module, span of A hat and B hat plus C hat and D hat, we notice that all four vertices, A, B, C, and D, are involved. So we're going to put red dots on the location of A, B, C, and D, and then we're just going to connect them with a red line. So this is how we're going to visualize the irreducible T modules, by how they're located on the graph instead of actually looking at the vector space itself. Okay, so this is an example of a 2 cube, and here's an example of a 3 cube. So we have a 3 cube, and let's say we fix a vertex on the right, and then the question is, how are the irreducible T modules going to look like? And this is how they look. So I haven't actually written down what the vector spaces are spanned by because it's going to be super long. But the takeaway is we're going to have 3 types of irreducible T modules in this case. One type is where the irreducible T module spans from all the way from the left to the right. And then we're going to have 2 copies of irreducible T modules that are different, but they're T module isomorphic. Sorry. They are vector space isomorphic, but they're 2 different irreducible T modules. And they will be located bang in the middle. So the 3 vertices that are, like second to the left, and the vertices that are second to the right. Okay, now one thing we notice about these irreducible modules and these irreducible modules is that they're kind of like bang in the middle. They seem rather symmetric, whatever that means. Okay, so now the question is, are they always symmetric? Now, here's a fact. For any D cube, for a positive integer D, the irreducible T modules of a D cube are always symmetric. Now, we haven't actually defined what symmetric means, like we've only seen it visually, but later we're going to define more formally what the symmetry means. But I guess the moral of the story is for the cubes, we see that the irreducible T modules are going to be bang in the middle. Okay, so the question is, for any distance regular graph gamma and a picked vertex x, are all irreducible T modules with respect to x symmetric? And if the answer were yes, the life would be very nice, but unfortunately the answer is no. So what that means is that there exists a lot of distance regular graphs where the irreducible T module is going to be tilted to the left or to the right. And later we're going to see that it's only one or the other. Okay. Okay, so some counterexamples would be the Johnson graph and the main topic of the talk today, which is the Grassmann graph. Okay, so let's have the symmetry in mind. Like, let's think about the question of symmetry in mind, and let's actually switch gears to talk about the Johnson graph and the Grassmann graph. So again, the main topic is going to be the Grassmann graph, but in order to understand the Grassmann graph, it's actually better to define Johnson graph first, and then draw the analogy between the Johnson graph and the Grassmann graph. So we're going to start with the Johnson graph. Okay, so here's a definition of a Johnson graph. All right, so let n denote a positive integer greater than 1, and let the set S be 1, 2, 3, 4, all the way to n. Okay, let L denote the set of all subsets of S. So you'll notice that the set L actually, together with the inclusion partial order, is going to form a poset, and we call this a subset lattice. And the definition of a Johnson graph is as follows. So let D denote a positive integer such that n is strictly greater than D, which is greater than or equal to 1. The vertex set of the Johnson graph, which we denote by J and D, consists of the D subsets of S. So it's going to be the subsets of S that has size D. And 2 vertices Y and Z are considered adjacent whenever their intersection has size 1 lesser than D. Okay, so let's have a look at an example. So this is an example J for 2. So at the top of the subset lattice, you notice that we have a set 1, 2, 3, 4. And then we're basically looking at the 2 subsets of 1, 2, 3, 4. So we're looking at the 6 element or the 6 subsets that we have bang in the middle. So these 6 subsets are going to be the vertex sets or the vertices, the vertex set of the Johnson graph, J42. And then as you notice, for example, 1, 2, and 1, 3, they have intersection just 1. So in the graph, you would connect 1, 2, and 1, 3 with an edge, and then so on and so forth. So this is what the graph is going to look like. And as you can see, 1, 2, and 1, 3 are connected, or they're adjacent. Another example could be like 1, 4, and 3, 4 are adjacent because they share an intersection of 4, and then so on and so forth. So we have J42, also aka this is an octahedron, if you kind of like switch the perspective. Yeah. All right, so we have an example of a J4-2. Okay, now what I'm going to do here is previously we had this subset lattice that looks like this, and now it seems like the subsets are kind of like everywhere, and like we have a bunch of lines going on. So what we're going to do is we're actually going to rearrange them into a nice rectangular picture so that we can actually see this, visualize this nicely. So here's the definition. We're going to partition L into the sets Lij. So I is going to be between 0 and d, and j is going to be between 0 and n minus d, so that Lij consists of those elements in the subset lattice such that the size of the subset itself is I plus j, and the size of S intersect X is j. So maybe I should have started with, we pick a vertex X, we pick a certain vertex X, and then we partition the subset lattice L based on the size of the intersection with X and the size of the subset itself. And the bottom comment here is basically just saying that we partition L into a disjoint union of the Lij's. Okay, so here's going to be a diagram. What we do is we're going to set X to be 3, 4. That's the vertex that we fix. And that's going to be on the right. And then we basically placed everything in the subset lattice into a nice rectangular picture. In this case, it's a square because we're looking at a 2 by 2. But basically what happens is at the bottom, we have the empty set. At the top, we have the whole set. But here's the thing. So let's point out, for example, the subset 1, 2, 3. For 1, 2, 3, its intersection is going with 3, 4 is going to be just a singleton 3. And the set itself has size 3. So it's going to have a dimension 1 and 2. So because 1 plus 2 is 3. So yeah, and based on that mechanism, we're going to place every subset in the subset lattice into this nice rectangular picture.
Can you do another one?
Oh,
describe why something else on this picture is where it is.
Oh, okay, sure. Right. So, for instance, I guess we can try to choose what's
3, 4.
Yeah,
1, 3, 4.
Yeah. Okay, we can do 1, 3, 4. So, for instance, 1, 3, 4, its intersection with 3, 4 is actually 3, 4. So, that intersection has size 2. So that's why the first coordinate is going to be 2.
Yeah.
And then 1, 3, 4 itself has size 3. So 2 plus 1 is 3. So it has the second coordinate 1.
So you just make up the rest of the distance going the other way.
Exactly. Exactly.
The rest of the size.
Yeah, the rest of the size. Exactly.
Okay.
Yeah. So that's what we do with the subset lattice to make this look nicer.
Cool.
Okay, so we just talked about the Johnson graph. Now what I'm going to do is we have a Johnson graph. We talked about the subset lattice. We're going to do exactly the same thing, but with the Grassmann graph. Okay, so we now turn our attention to the Grassmann graphs. Okay, so the definition already it seems rather difficult, but all right, let's see. So let FQ denote a finite field with Q elements. Okay, let N denote a positive integer, and let fancy V denote a vector space over the finite field FQ that has dimension N. So we were talking about the set of size N for the Johnson graph. For the Grassmann graph, we have a vector space over a finite field that has dimension N. Okay, now let P denote the set of all subspaces of the fancy V. The set P together with the inclusion partial order is going to form a poset, and we call this a projective geometry. So just like how we had the subset lattice, we have a projective geometry in this case. Okay, now how do we define the Grassmann graph? Let D denote a positive integer such that N is greater than D, which is greater than or equal to 1. The vertex set of the Grassmann graph, and we denote this by J sub Q and D, so we have the extra parameter Q, consists of the d-dimensional subspaces of the fancy V. And the two vertices YZ are adjacent whenever their dimension is 1 lesser than D. So now you can see how from the Johnson graph picture, we basically translated everything to the Grassmann graph picture where we change all the sets into the subspaces. Okay, so let's go through one example, one or two. So here's an example of a 3D vector space. And let's say N is equal to 3 and D is equal to 2. So what we're doing is the vertex set is going to consist of a 2-dimensional vector spaces. Okay, and for the sake of simplicity, let's just assume that Q is equal to 2. Okay, in that case, let's think about a 2-dimensional subspace. So we can have this purple space at the bottom, or we can have like a 2-dimensional subspace that goes like this. All right, and in that case, the intersection of any two 2-dimensional subspaces would be a one-dimensional subspace. So in the case of n is equal to 3 and d is equal to 2, any two vertices are going to be adjacent. So we actually have a complete graph of 7 vertices. So each vertex here is going to represent a two-dimensional subspace. And the two vertices are adjacent whenever their intersection is a one-dimensional subspace. And in this case of n is equal to 3 and d is equal to 2, unfortunately, we're going to have a complete graph, which we've seen a lot before. So the next smallest example that does not have a complete graph structure is J242. And unfortunately, there isn't a nice representation, or there isn't a nice picture of this graph, because already we have 35 vertices and it has a common valency of 18. So if I actually draw it on a screen, it's just going to be like a bunch of vertices and a bunch of lines, and it's going to be really hard to analyze. But yeah, basically I guess the takeaway is the Grassmann graphs are going to be really hard to draw. But yeah, if anyone manages to come up with a nice picture of a J242, please let me know. I guess I'll buy lunch. All right. Okay, so just like what we had for the subset lattice, we can actually do exactly the same thing for the projective geometry. So we're going to define P sub ij. So we're going to pick a vertex X, and then we're going to partition P into these sets Pij, such that the dimension of U, so U is in P, such that the dimension of U itself is I plus j, and the dimension of U intersect X is going to be j. Wait, was that supposed to be j or I? I think I think that's a typo. That's supposed to be an I. Yeah, that's supposed to be an I. We have a picture here, so hopefully that's good. Yeah, it's supposed to be I. That's a typo. Okay, so just like how we had the rectangular picture for the subset lattice, we have a projective geometry right here. Let's say we have an element in Pij, which is located right here. In that case, we see that the intersection between U and X is going to have dimension I. So the first coordinate is going to be I, and then the dimension of Pij is going to be I plus j. So that's why the second coordinate is going to be j. So what we did was we grabbed every possible subspace or every possible element in the projective geometry, and we placed it in a nice rectangular picture. Okay, so now the question is, why do we do this? Like, what is the point of having the projective geometry in the nice rectangular picture? And the answer is, this is going to be a nice way to represent the irreducible T modules in the Grassmann graph. Okay, so let's go through some more preliminaries before we actually talk about the irreducible T modules. Okay, so from now on, we're going to write gamma to be the Grassmann graph J, Q, and D. And it is known that gamma and J, Q, and n minus D are graph isomorphic. So you can think about it as we have a projective geometry. We have a d-dimensional subspaces. And if you actually flip that projective geometry by a complement, by a complement for any inner product, you actually see that the n minus d-dimensional subspaces and n-dimensional subspaces, they're going to be graph isomorphic. So without loss, we're going to assume that n is at least 2D. Okay, now the case n is equal to 2D is actually rather special. So until further notice, we're going to assume that n is strictly greater than 2D. Later in the last slide or something, I'm actually going to talk about the case n equals 2D. And it's going to show you a result on why this assumption is actually quite important. Okay, so like I mentioned, to study the graph gamma, the Grassmann graph, and its irreducible T modules, it's actually important to study the projective geometry P first. So what we're going to do is we're going to look at a bigger picture with the projective geometry, and then we're going to focus on the Grassmann graph, which is just going to be a d-dimensional slice of the projective geometry. Okay, so just like how we defined mat XC, we're going to define mat PC, which is a matrix algebra where the rows and columns are indexed by the projective geometry P. So now the rows and columns have all the possible subspaces of the projective geometry. Okay, let psi denote a C vector space consisting of the column vectors with rows indexed by P and all entries in C. So just like how we had a vector, a vector space V for the graph, we're going to have a vector space psi for the mat PC. Okay, and as you can see, the algebra mat PC is going to act on psi by left multiplication. And the mat PC module psi is called standard. So in this case, it's a standard mat PC module, just like how V was a standard mat XC module. Okay, now our general goal is going to be to define what is called a subalgebra H of mat-PC and study the irreducible H modules. So in the graph, we had the mat-XC, and we looked at its subalgebra T, the Terwilliger algebra. Just like that, what we're going to do is we're going to see a subalgebra H of mat-PC, and we're going to study the irreducible H modules in psi. Okay, so here's a quick lemma, and this has a diagram later on. So let U, V, and P such that U is contained in V, and the dimension of V is equal to dimension of U plus 1. So for those who study like posets and those incidence structures, we usually call this V covers U. That's like a common phrase that we use. Okay, now we're going to write U to be in Pij and V to be in Pln. Then either L is going to be 1 greater than I and N is equal to J, or N is going to be 1 greater than J and L is equal to I. So let's actually go through this using a diagram. I think that's much easier to understand. So here's an example of V slash covering U. So if V and U, their respective location is as given, and if U is contained in V, then we say that V slash covers U. And if V and U's respective location looks like this, then we say that V backslash covers U. Yeah, and basically the previous lemma was saying we can only fall into one or the other. If U is contained in V, and if the dimension of U is 1 lesser than V, then U is either slash covered by V or backslash covered by V, one or the other. Okay, now just like how we defined the Bose-Messner algebra, the dual Bose-Messner algebra, and the Terwilliger algebra, we're just going to define a bunch of matrices that define the subalgebra H. Okay, so we define E star ij, so this has a double index. This is a diagonal matrix in mat-PC where the UU entry is 1 if U is in Pij, and 0 if U is not in Pij. So it's just like that EI star that we saw for the graph, but then in the projective geometry picture. Okay, now we define some more graphs, some more matrices. Okay, so we define diagonal matrices K1 and K2 as follows. The exact details are actually not that important. I guess the takeaway for these matrices are we're just trying to define a matrix algebra that is similar to a Terwilliger algebra T. Okay, so we have diagonal matrices K1 and K2. And we have some other matrices, L1, L2, and R1 and R2. And they are defined as follows. So for example, L1 has UV entry 1 if V slash covers U and 0 otherwise. L2 has UV entry 1 if V backslash covers U and 0 otherwise. And then R1 and R2 are simply going to be their transposes. So looking at the diagram, so this is an example where the UV entry of L1 is going to be 1. This is when the UV entry of L2 is going to be 1. And then R1 and R2 are just going to be their transposes. Okay, so basically the moral of the story is we basically have a tool that allows us to go from one subspace to the other. Just like how the adjacency matrix allowed us to go from one vertex to another. And here, these L1, L2, R1, and R2, they allow us to go from one subspace to another. Okay, and we're going to denote, we're going to denote this subalgebra generated by L1, L2, R1, R2, and then the K1 and K2 and their inverses by the fancy H. So fancy H is going to be the subalgebra that is generated by these 8 matrices, and this is kind of going to be like the analog of the Terwilliger algebra T, but in a projective geometry picture. Okay, so we recall the standard module psi. And by construction, the psi is going to be an H module. So H acts on the vector space psi. Okay, and again, irreducible module stuff. So let omega denote an H sum module of psi, and we say that omega is irreducible whenever omega does not contain an H sum module besides 0 and itself. And just like how we had for the Maschke's theorem, the standard module psi is a direct sum of irreducible H modules. Okay, and here's a very long lemma. This is a result by Watanabe in 2017. So what this lemma does is this actually describes the irreducible H modules in psi. So let omega denote an irreducible H module, then there exists 3 integers alpha, beta, and rho such that the following hold. So part 1 basically just gives us the inequality on rho, alpha, and beta. I guess one takeaway is that rho has to be non-negative. And you'll see in a diagram in the next slide why these are actually quite important. And the second one is saying that if we have a certain irreducible omega, and if we slam an E star ij, so if you look at just a single I comma j, so as a single location in the projective geometry, then its dimension is actually just going to be 1 or 0. Okay, so here's a diagram that describes the irreducible H modules. So just like how we had for the irreducible T modules on a graph, we actually located a bunch of red dots and then we connected it with a line. In the projective geometry picture, we actually have a red rectangle. So for each irreducible H module, you can actually locate where those subspaces are going to be that are contained in that irreducible H module. So and then we had 3 parameters, alpha, beta, and rho. Alpha is going to be the distance, what do you call it? It's the southwest distance. And then beta is going to be the northwest distance. And then rho is basically this index that tells us how shifted this red rectangle is to the left. And one thing we notice is that we recall that rho was non-negative. So what that means is it is possible for this red rectangle to be shifted upwards or shifted to the left, but it can never be shifted downwards or shifted to the right. So there's actually a nice bias going on here. Okay, some more definitions. Let omega denote an irreducible H module. We call the 3 numbers alpha, beta, rho the type of omega. And this is a result by Liang, Ito, and Watanabe in 2020. For each triple alpha, beta, and rho that satisfy the conditions that was given in Watanabe's lemma, there exists an irreducible H module of type alpha, beta, rho, and this is unique up to isomorphism. So if you give me alpha, beta, and rho, there's just one irreducible module that is unique up to isomorphism. Okay, so now we're going to link the algebra H and the algebra T. So if you recall, we had the projective geometry picture, and then we had a red rectangle in the middle. And what this does is we're going to slice through a d-dimensional, we're going to look at the d-dimensional slice. So that's basically what we're doing. Okay, recall the mat-PC module psi and the mat-XC module V. So V can be considered as a subspace of psi in a way that V is only looking at the d-dimensional subspaces over the whole projective geometry picture. Okay, in the sense that V is isomorphic to this expression right here. Okay, so we're going to use the following notation. For an H submodule omega, let omega tilde denote a subspace of V that is defined by the restriction of this thing to V. So basically what we're doing is if we have an H submodule omega, we're just going to slice through a d-dimensional slice. Okay, I think I'm going to have diagrams after this. So, okay, the lemma, lemma by Liang, Ito, and Watanabe in 2020 says that if omega is an irreducible H module, then omega tilde is an irreducible T module of the Grassmann graph gamma. Okay, and here we have the diagrams. So we recall that the red rectangle represents the irreducible H modules, and the dashed line is a line across the d-dimensional subspaces. And what we have is that the double-headed arrow is going to represent the location of the irreducible T module of a Grassmann graph. So this is one example, this is another example, and this is another example. And one thing we notice from here is that this would be an example where an irreducible T module of a Grassmann graph is not bang in the middle. So this is an example where an irreducible T module is no longer symmetric with respect to the graph. Okay, so now I think we're ready to talk about the displacement, which is talking about how far off is the irreducible T module from being symmetric. Okay, so like I said, we observed that the T modules are not necessarily symmetric, and now we describe the symmetry using the notion of a displacement. Okay, and this is where we start to get a little technical here. But yeah, so we define the displacement. So before we define displacement, we're going to introduce the primitive idempotence of gamma. All right, so here are the technicalities. Okay, so we're going to use the notation bracket L to mean the Q binomial that looks like the following. We have Q to the L minus 1 over Q minus 1. For those who are familiar with the Q binomial coefficients, this is just Q choose 1. This is just L choose 1 sub Q. Okay, now for I between 0 and D, we're going to define theta I to be that expression right there. And then these are actually eigenvalues of the adjacency matrix A. Okay, and we're going to define EI as the following. So the exact details are not that important, but the takeaway is that these EIs are somewhat like eigenmatrices of the adjacency matrix A. So you can think of it as like A times EI is going to give you theta I times EI for I between 0 and D. Okay, and we call EI the primitive idempotent of A associated with the eigenvalue theta I. And one remark is that we have another name for EI star, and it's called a dual primitive idempotent with respect to a vertex X. So the takeaway is that the idempotents EI and the dual idempotents EI star, they actually behave in a similar manner. What the exact behavior is, we can talk about it afterwards if you have any questions on this. Okay, but now we start to give parameters for the irreducible T modules. Just like how we have for the irreducible H modules, we start to have parameters for irreducible T modules. So if W is an irreducible T module, we say W has an endpoint R whenever the minimal value of I such that EI star W is non-zero. That's going to be our endpoint R. And then dual endpoint T is going to be the minimal index I such that EI W is non-zero. And the diameter is going to be the number of i's where EI star W is non-zero minus 1. So let's have a look at this using the diagram. Okay, so again, omega is our irreducible H module, and this double-headed arrow is our irreducible T module. R, which is the endpoint, is going to be the distance between this red rectangle and the fixed vertex X. And then T is going to be the dual endpoint, which is the distance between the 0 subspace and the bottom of the irreducible H module. And then D is simply just going to be the length of the irreducible T module. So yeah, one thing that can be a little confusing is this small d is also called a diameter, but the lowercase d represents a diameter of an irreducible T module, where the capital D represents the diameter of the whole graph. So there's a distinction. Okay, now here's the definition. By a displacement of an irreducible T module W, we mean the integer r plus t minus capital D plus d. Okay, so going back to the diagram, basically we're looking at this value t minus this quantity here on the left. And one lemma is that the displacement is always non-negative. So what that means is this dual endpoint will always have to be bigger than the distance on the left. So that represents how the irreducible H module will have to be, it has to be shifted upwards or to the left, but never to the right and never downwards. So lemma by Terwilliger 2024 says that the displacement has to be non-negative. Okay, now we started off with a question of when is the irreducible T module symmetric? So here's a lemma by Terwilliger 2024 that says if W is an irreducible T module with endpoint, dual endpoint, and diameter, such that the displacement is equal to 0, meaning if it's actually symmetric, then R is equal to T. So the endpoint and the dual endpoint are the same, and the diameter of the whole graph is the diameter of the irreducible T module plus 2 times R. So another way of saying the irreducible H module is like bang in the middle. Okay. Now we're ready to define the nucleus. So by the nucleus denoted by n of gamma with respect to x, we mean the span of the irreducible T modules that have displacement 0. So basically, we're collecting all the irreducible T modules that have displacement 0, the ones that are symmetric, and then we smush them together, and then we form a nucleus. Okay, so now what we're going to do is we're going to describe the nucleus n of gamma. So we continue to fix a vertex x. Okay, here's one definition. We say that an irreducible H module omega is alpha dominant whenever omega has type alpha 0, 0 for alpha between 0 and d over 2. I came up with that name, by the way. Yeah, so we're going to see a diagram that represents an alpha dominant irreducible H module. Okay, but here is a theorem by Lee, Park, and myself. There is a one-to-one correspondence between the following two sets. So if we look at the irreducible T submodules of N, and if we look at the irreducible H modules that are alpha dominant, there's actually a one-to-one correspondence. So here's a diagram. This is what an alpha dominant irreducible H module would look like. So the top left and the bottom right would stick to the edge, and then the bottom left and the top right, their distances are going to be exactly the same. That way, if we slice it through a d-dimensional slice, this irreducible T module is going to be bang in the middle. Okay, so we established a one-to-one correspondence between the irreducible H modules and the irreducible T modules. So what that allows us to do is it allows us to find the dimension of the nucleus. So the dimension of the nucleus is given as follows. So it's going to be the sum of d choose I sub q. So it's a q binomial coefficient. The exact number, if you actually stare at it for a while, you might notice that it's actually the same value as the number of subspaces of X. So X is this d-dimensional subspace, and the total number of subspaces of X is going to be that sum of d choose I sub q. So what that allows us to do is it actually allows us to describe the basis of a nucleus N in a nice way. Okay, so now our goal is to describe the basis of the nucleus. Okay, so we're going to pick a subspace alpha that is contained in X, and we define the following vectors. We have alpha check, and we have alpha to the power of N. And alpha check is going to be the sum of y hats, where y contains alpha, and alpha to the n is going to be the sum of y hats, where the intersection of x and y is exactly alpha. So using a diagram, this is what it looks like. So we have a subspace alpha that is contained in X. Then alpha check is going to be the sum of the y hats, where y is a vertex that lies in this location and contains alpha. And then, alpha to the power of n is going to be the sum of the y hats, where y's are the vertices in that blue dot and contains alpha. So we have some sets of vertices. And here's a theorem by Lee, Park, and myself. Each of 1 and 2 below forms a basis for n. So we grab alpha check for all the possible alphas that are contained in X. That forms a basis for the nucleus n. And the second set of basis is alpha to the n, where alpha runs from 0 to X, basically. Alpha is contained in X. So these two are going to be, these two are going to form bases for n. And this theorem is our main result. Okay, one last slide. So earlier I promised that we're going to talk about the case n equals 2d. Okay, so we have that theorem about one-to-one correspondence between the alpha dominant H modules and the irreducible T modules that are inside the nucleus. Now, unfortunately, for n equals 2d, this one-to-one correspondence fails. So for a given irreducible T submodule of a nucleus, there actually exists a non-alpha dominant irreducible H module that gives you that irreducible T module. So there's, unfortunately, it's kind of like many to one. It's not 1-to-1. So the problem is, what happens when n is equal to 2d? Find the dimension of n. And the second problem would be, if we know the dimension of n, then what would the bases look like? So that's our second problem. But that's it for my talk. Thank you for your attention.
All right. Any questions in person? Or on Zoom? Or in person?
Go Zoomers.
Oh. On Zoom, anyone?
We have clap.
All right. Carrie's going to ask a question here.
I'll shout it loud so you can hear it. No. So that rectangular arrangement of either the lattice or the subspaces or whatever it sets.
Yep.
Is that just in this work, or where does that come from? I haven't seen that.
So let's see. I think the most natural version would be doing the same thing for the graph. So on the graph, what we do is we fix a vertex and we place it on the right, and then we actually locate all the other vertices depending on their distance with X.
Yeah. Is that from like your work, or is that from some other? Is that in this field that came up, or is that like from where that came from, or?
That's a good question. Like, when did I start using it?
You almost invent. Is that just your terminology?
The projective geometry, the term exists.
So then the rectangular arrangement, the rectangular arrangement, that one.
That's a good question. So I first
just go back to this.
Yes. So we're talking about this slide. Well,
I mean, throughout your talk,
right here,
the rectangular arrangement first for the Johnson, then you have.
Yeah, the Johnson graph,
then you
yes.
have also the rectangular arrangement. in
Right.
Space. So I
Yeah.
was wondering if that is when you all do it, or that's from.
So my guess is that this is actually, oh no, this is actually definitely right, quite common in a way that it also appears in the Ito Liang Watanabe paper, and it also appears in the Watanabe paper. But yeah, Watanabe's this mathematician who does a lot with projective geometry, and he also includes like a lot of diagrams that look like this rectangle.
They do that, okay.
Yeah.
And Terwilliger.
Yeah, Terwilliger, yeah. He also does something related to this. The only difference is that in Watanabe's paper, the rectangle is not tilted like this. It's actually like an actual upright rectangle. So yeah, I had to do a lot of work like translating between the upright rectangle and the tilted rectangle. But yeah, I think it's a common technique that we use in order to study the Grassmann graph.
Is there any connection to the Grassmannian?
Oh, okay. Yeah, that's a very common question that I get. But you can think of it as like, so Grassmannian is over either the reals or the complex, I believe, right? It's a manifold over the real or the complex. And the Grassmann graph, you can actually just think of it as like, what happens if the field becomes discrete? It's like a discrete field version of the Grassmannian. So yeah, you can think of the Grassmann graph to be like that. Yeah, so I can expect something that is true in Grassmannian, and then like you're restricted to discrete. It could be true, but then yeah, the real question is like something that is true in the Grassmann graph. Can we extend it to like a manifold version? I don't know. It's gonna be a hard question.
So when people think of a nucleus, is it because it's somehow the displacement being zero makes it more symmetric?
Yeah, basically, yeah. So displacement zero means the irreducible T module is going to be like bang in the middle, and then we're basically grabbing all those displacement zero T modules, and then we're taking a direct sum of those. So yeah, so for the name is by Paul Terwilliger, and yeah, I think it was just the fact that it's from like displacement zero and like it looks symmetric. I think that's how I came up with the name.
Any other questions? All right, if not, let's thank the speaker again.
Right, thank you.